All right, so let's take what we've learned so far and see if we can work this problem. So again, I want to draw the shear force and the bending moment for this problem. I've got a 600-pound force right in the middle of the beam, and I've got an applied couple here on the right side. So the first thing I want to do is find my reactions. So what I'm going to do is I'm going to come over here at A, and I'm going to assume I have a positive shear at A, and I have a positive shear at B. I'm drawing both of my shears in their positive sign convention. And I'm going to find those values. So there's a lot of different ways to do it. I need to sum moments at probably either A or B. I'll just do it at A. We'll do it alphabetically. So if I sum moments at A and set it equal to 0, I'm looking about the moment produced by this 600-pound force, this applied couple, and then this shear force. We'll start with the force. What kind of moment does that create? Positive or negative about A? I'm using right-hand rule. Is that? Looks like it's really. Is that better?
Yeah, you can see it.
Is that better? It looks kind of shiny. Maybe I just turn the light off. Is that better? Oh, I think that looks better, doesn't it?
Yeah.
Okay, cool. We'll do it that way. All right, so the 600-pound force creates negative moment, so I'll have 600 pounds, and the moment arm is 10 feet. I'm summing moments about A. Right-hand rule is my sign convention. What kind of moment does this 4,000 produce? Positive or negative? Negative, so that'd be negative 4,000 pound-feet. And then I have the reaction, the shear at B. What kind of moment does that create? Negative. So the shear at B creates negative moment, and that has a moment arm of 20 feet. So I should be able to solve for the shear at B. I want to say that's going to be, let's see, that's 6,000, that's 10,000, 5,000?
No,
500.
Yeah.
Negative 500. That sounds reasonable. So the shear at B is negative. And then if I sum forces in the y direction, make sure that's in equilibrium, what do I have? Well, my shear force at A is up. My shear force at B is down. I also have acting down a 600-pound force. And what else? Nothing. So I'll solve now for the shear at A. So I plug in my 500 here, the signs cancel, and it ends up looking like I get 100. Does that look right? And that comes out to be positive shear. I found my shear reactions. So I'm going to come over here to my structure, and I'm going to sketch a template. There's my left side. There's my right side. So there's the boundary of my problem. I'll go ahead and for my shear force, add a positive x value. I'll assume my shear is up here, and all my units are going to be in pounds. Also, I'll notice that there's an applied load here. That's probably going to be an interesting point, so I'll add that to my template. Also, I've got an applied moment. That might affect something too down the road, so I'll add that to my template. So that's a good starting spot. So remember, the first thing we do is we'll put on our shear value. So starting on the left-hand side, looking at the shear at A, I have a value of 100. When I get to the right-hand side, my shear at B, what should my value be? negative 500. Again, I have my starting spot and my ending spot. Also, I've got my relationships. I know that the change in shear between any 2 points is the area under that portion of the load curve. And then also that the slope of my shear diagram is equal to the value of the load. So let's take this one first and apply it. Now, remember this point load, I know what's going to happen at the point load. What's going to happen? My shear is going to change instantaneously that amount. So let's look at the section right before it, just to the left. So what's the load just to the left? If you were to kind of cover that up, what do you see here? Nothing. Load is 0. So the area under 0 is 0. So I should, if I start at 100, I should at that sec stop at 100. And then the slope of the load, the slope of the shear diagram is equal to the load, and just as we mentioned before, the load is 0, so I have a 0 slope. 0 slope is horizontal line. So it looks like the shear over the first 10 feet is constant and equal to 100. Now as I go from the left to the right side of this point load, what happens? The shear changes exactly how much? 600, and it's down, so that's negative. So 100 minus 600 is minus 500. Now the change in shear between these 2 points should be the area under the load curve again. So let's look up here and see what we see. What's the force load between the midpoint and B? Don't be distracted by this moment. Moment is not a force. So there is none. So again, that means there's no change. If you start at 5, negative 500, you end at 500, great, it matches. And then the slope of that curve is equal to the load, and the load again is 0. So we have 0 slope. So there's your shear diagram. So what's the maximum shear and where does it occur? Maximum shear is negative 500 and occurs anywhere in the second half of the beam. So any questions about that one? So let's add to that. Let's do our moment. So I'll apply, there's my x direction, there's my positive moment. All these values will be in pound feet. All right, what's our starting point here? To go up, A, what's the moment at A? 0. Over here at the end point, do we know something about the moment here? Well, yes, since it's there's no cantilever section, we know that this moment is also 0. So we know where we're going to start, we know where we're going to end. So now we're going to apply the relationships that the change in moment is what? The area of the shear diagram. Look at our shear diagram. Nice rectangular areas. That shouldn't be too big of a problem. And also that the slope of our moment diagram should be equal to the value of the shear. So now applying this first to the relationships, you can see there's a nice chunk of shear that I can deal with here. So let's just worry about this first 10 feet. So what is the area under the shear diagram over this first 10 feet? Well, rectangle, it's base times height, so 10 feet times 100 pounds, it's 1,000, right? So I'll end up with a value of 1,000. I won't write it in just yet. And what's the slope of that diagram? It's equal to the shear. And what's the shear everywhere? Constant and positive. So it looks something like that. So this would have a value of 1,000. Now what happens next? Well, I move over here and I start looking at this area. Now there's one other thing we got to pay attention to is what? We've got an applied moment. So let's just worry about this first part up to the applied moment, which I'll just mention here again. This is 5 feet. So I'll double hatch this one to make it stand out a little bit. So what's this part of the curve? Well, again, it's base times height, so that's 5 times, excuse me, negative 500. That's negative 2,500. So if I start at 1,000 and I subtract 2,500, what do I get? Yeah, negative 1,500. And what's the slope between that point? Well, according to our relationship, it's the value of the shear. The value of the shear is constant and negative. So here's a constant negative slope. Now what happens? Well, as I go from the left side to the right side, my moment equation is going to change based upon this slope. And a clockwise applied moment creates a positive jump. So I'm going to add 4,000 to the negative 1,500 and get what? 2,500. Now the change in moment over the last 5 from 2,500 to 0, I know it better come out to be 0, so let's see what that is. So that part of the curve would be this part. And that's, again, it's a rectangular section, so base of 5, height of negative 500, that's negative 2,500. Well, that's great. I'm starting at 2,500, I subtract 2,500, I get 0. Everything matches. And then the slope is equal to the shear. The shear is constant and negative, so I get constant negative value. So there's my moment diagram. So in this particular problem, what is the maximum bending moment in the beam? Looks like it's positive 2,500 and it occurs just to the right of the applied couple. There's actually a point in the beam where the moment is 0. That's a transition from a positive moment. What shape would the curve of the beam curve into with a positive moment? Kind of a smiley face, and then into a negative, and then back into a positive. So this thing is going to do all kind of twisting as we go along. It's because of this moment. Just so that you'll maybe it might help you, it may not. I'll write on here that the slope here is actually, obviously this is not to scale. It's 100 to 1. The slope here is minus 500 to 1. And here, minus 500 to 1. Any questions about that? That's a testable problem, I think.